So this is our circuit design in the lab. So this is the connection of the ECG to the instrumentation amplifier, and this is the connection of the instrumentation amplifier to the right leg drive circuit. So this one is the connection from the instrumentation amplifier to the bandpass filter, and this is the connection from the bandpass filter to the notch filter. So the output after the notch filter will be connected onto the oscilloscope. So now we will demonstrate on the relation of the electrode to the machines. So as you can see, one of the connection will be connected to the right hand of the patient, and electrode will be connected to the left hand of the patient. So the third electrode will be connected to the right leg of the patient. So now, after we have already connected all the electrode, we will analyze the output result by using the oscilloscope.
Good day to Dr. Yazid. We're from Group 3. We'll be present the ECG biosignal instrumentation system. Our group members including Muhammad Hisham bin Iyas, Muhirwan Kunja'u, Muhammad Afiq Iqmal bin Zainuddin, and Nur Alia Diana binti Muhammad Ismail Habdi. The table of contents including the introduction, objective, methodology, results, discussion, and conclusion. I'll be starting off by the introduction. In electrocardiography, ECG or EKG is a non-invasive diagnostic method used to monitor the heart's electrical activity over time. ECG produces a graphical output that reflects the heart's overall health, rhythm, and rate. It is essential for identifying conditions such as arrhythmias, heart artery blockages, and myocardial infarctions. The ECG waveform consists of distinct components such as the P wave, QRS complex, and T wave, each indicating different stages of the cardiac cycles, as shown in the figure. ECG is a vital tool in cardiology used to identify ischemia, arrhythmias, and other heart abnormalities. Medical professionals rely on ECG traces to assess the heart's conditions, evaluate treatment effectiveness, and guide further research. The objectives of the project is to develop a simple biosignal instrumentation system specifically for ECG signal recording. Secondly, to create a system that can accurately capture and process the ECG signals through effective amplification, filtering, noise reduction, and closely resembles the input ECG signals. And finally, to compare different circuit designs to determine the most cost-effective and efficient solution for ECG signal processing.
Hi, Assalamualaikum. I'm Hisham, representing about the methodology of this assignment. Since we need to design ECG subcircuit, let me review a bit about what ECG subcircuit is. ECG subcircuit is a sensory electronic circuitry with biomedical instrumentation and electronics that is in charge of obtaining and processing the electrical signals from the body in order to produce an accurate ECG waveforms. So our methodology consists of these flows of steps, which we need electrode, instrumentation amplifier, bandpass filter, stop or notch filter, right leg drive circuit, and AC converter. Electrode is used to detect electrical impulses generated by the heart during cycles of contraction and relaxation. And then connect it to instrumentation amplifier where it amplifies the key signals, and then connect it to bandpass filter, which again makes frequencies outside of its operating frequency range while permitting signals inside it to pass through. And then we connect to bandstop or notch filter to attain the frequency within a specific range while passing all other frequencies unaltered. The purpose of right leg drive circuit is to lower interference and common mode noise in the AC signals. And lastly, we will connect to AC converter, which we use oscilloscope to convert analog signals to digital data for analysis and display. And this is our instrumentation amplifier circuits, which we use to amplify raw AC signals with an instrumentation amplifier we use, which is INA128E, to raise the signal's voltage levels. And our gain chosen is 251 gain. And next, we connect to passive band pass filter circuits to isolate the phase frequency range of the AC signals. The purpose of high pass filter is used to eliminate the offset developed between electrodes. Meanwhile, the purpose of low pass filter is used to remove high frequency noise. And our passive band pass frequency range is between 0.005 Hz and 100 Hz. And then the output will be connected to the notch filter or non-S-band stop filter. This is our notch or non-S-band stop filter circuit. It is used to remove a particular frequency from AC signals such as our interference. Since we live in Malaysia, our interference is 50 Hz, so we need to remove the 50 Hz of our interference by using this notch filter circuit. And not to forget, we also implement right electric circuit, which used to lower interference and common mode noise in the AC signals. It works by actively cancelling out any interference that might obstruct biological signals and make them difficult to measure. So we use the right electric circuit to minimize common mode interference and make the signal easy to read. And all of these circuit will be combined, and this is the complete AC subcircuit design that we chosen. This is the ECG and electrode inputs, and this is the instrumentation amplifier. This part is our passive band pass filter. This part is notch and bandstop filter, and this is the right electric circuit. The output of the notch filter will be connected to the ADC converter, which we use oscilloscope. And this is prototype of our designs. This is right leg, instrumentation amplifier circuits, band pass filter and notch filter, and the output of notch filter will be connected to the ADC converter, which is oscilloscope. And this is how we test our prototype. We use electrode, we connect to left arm and right arm, and the right leg circuit, we connect the electrode to the right leg of the patient or our subject. And that's for methodology. I will pass my teammates to explain about our results obtained.
Now let's move on to the result part. We have a total of 5 designs. So this is the first design. In this design, we are using instrumentation amplifier, passive pass filter, notch filter, and also driven right leg circuit. So this is the output from the transient analysis and also the virtual oscilloscope. It can be shown that the ECG signal is amplified on the oscilloscope. So for design 2, we use the same design, but instead of passive band pass, we use active band pass, and the result looks similar to the design 1. For design 3, we are also using the same design as design 2, but then we remove the driven right leg circuit. But when we see the output from the oscilloscope, it can be shown that the signal are not well captured. For design 4, we are using much more operational amplifier to know whether it has any difference towards the ECG signal, but instead we got a very weird ECG signal output coming from the design. For design 5, we are also using the same component, but the location of the notch filter are after the high pass filter, and the notch filter used here has a total of 3 notch filter, and after the notch filter we also have the amplifier. So the result looks similar to the ECG, but then the amplitude of the ECG signal is reduced. So for our prototype, we chose design 1 due to some reasons which I will explain later. So this is the frequency response result that we get. So this is the setup for the frequency response of band pass filter for our design. So this is the result we get from the simulation. So this is the result that we get from our experiment. So it can be shown that the cutoff frequency for the low pass filter will be at the 0.001 Hz, while for the cutoff frequency for the high pass filter will be at the 100 Hz. For notch filter, we also do the frequency response at the notch filter of our design. So this is the setup for the frequency response of notch filter, and this is the result that we get from the simulation. This is the result that we get from our experiment, and it can be shown that the cutoff frequency for our notch filter will be at 50 Hz, and it goes to show that our notch filter actually can filter out 50 Hz noise. So this is the output comparison that we get from design 1. So this is the simulation by using Tina, and this is our prototype that we get from the oscilloscope when we connect the oscilloscope to the output of the design 1. So it can be shown that the signal that we get is distinguishable but imperfect, as it does not show repetitive pattern like the simulation from Tina. So for the prototype cost and performance comparison, the main reason that we choose design one is that it has a very good performance in terms of its application and filtering of the ECG signal with a very low total cost. So that's why we choose design one. For design 2 and design 3, they both have the good performance and similar to design 1, but it has a slight higher in terms of cost. For design 4, it has the lowest cost among the 5 design, but then for the performance, it does not show what we want. And for design 5, it also has the output of the signal that we want, but then it has the highest cost among the 5 design. That's why we chose design 1 for our prototype.
Hello, my name is Alia, and I'll be discussing on the reasons on why we choose this circuit. So first of all, it is because of cost and efficiency. The INA128 provides a high-quality amplification at a reasonable cost. It also eliminates unwanted noise, as the 50 Hz notch filter is designed to target power line interference, and also it has a driven right circuit which cancels interference affecting both leads to improve the common mode rejection ratio CMMR to ensure the reliability of ECG signal acquisition. It is also accurate. It is also an accurate amplification of heart signal, which uses an INA128 instrumentation amplifier, which offers a high gain of 251. So I'll also be discussing the results analysis. So we obtain the graph as shown in this slide. So we have the necessary components of an ECG, which are distinguishable as labeled. There are 5 components which forms the peaks to a normal ECG waveform. So to achieve accurate and reliable ECG, relatively noiseless ECG signals are required. But in a real-life setting, various noises and artifacts often disturb ECG signals. So in our study, the frequency measured is higher than a normal ECG frequency. There are a few reasons, which could be due to enlarged or thickened heart muscle. Another reason is the frequency range of the motion noise, which ranges from 1 to 10 Hz. A power line interference PLI, which ranges from 50 to 60 Hz.
Good day, Doctor. I'm Jia. Now I'm going to present the discussion. First, we compare between the circuit design. Design 1 is made up of an ENA128E instrumentation amplifier, passive band pass filter, notch filter, and driven right leg circuit. Design 2 is made up of an ENA128E instrumentation amplifier, first order active band pass filter, notch filter, and driven right leg circuit. Design 3 is made up of an ENA128E instrumentation amplifier, first order active band pass filter, and notch filter. Design 4 consists of instrumentation amplifier, inverter amplifier, second order low pass filter, and a DC level adjustment circuit. Lastly, the components included in the design 5 are ENA333 instrumentation amplifier, low pass filter, high pass filter, and notch filter. Based on the comparison between circuit design in terms of cost consideration and complexity, design 4 is the cheapest, which is 22.5 ringgit. The circuit is the simplest and does not consist of right leg drive circuit. Design 5 is the most expensive, which is 76.11. It is very complicated and made up of many electrical components. This can show that when more electrical components are used, the more complicated and expensive the circuit. Each of the design circuit is simulated using transient analysis in Tina software. Based on the performance, design 4 is eliminated, although it is the cheapest because it has low performance. As shown in the table, circuit design 1 and 2 show better output, in which the noises are removed and the TQRST waveform of the ECG can be clearly seen. Among this design 1 is selected because it is the cheapest while being able to capture clean ECG output. Next, I will discuss about the weakness and improvement towards the proposed design. For the weakness, the circuit we design has limited flexibility in filtering. The passive band pass filter and 50 Hz notch filter, while effective, present fixed frequency responses. Furthermore, other weaknesses may include not so strong noise reduction techniques. Our proposed design is very hard to be worn by the patient due to inconsistent wiring of the circuit. Potential improvement for our circuit design includes the integration of wireless connectivity, enabling the real-time patient monitoring and facilitating remote healthcare application. Incorporating robust data storage mechanism would support prolonged ECG data analysis. For future iteration of the design, we can explore the integration of tunable filters to empower the healthcare professional to dynamically adjust the filtering parameter based on the patient's specific cardiac condition. This provides increased flexibility in managing diverse signal. Besides, we can implement machine learning algorithm and adaptive filtering techniques to autonomously analyze and adapt to the evolving noise pattern, which enhance the signal-to-noise ratio and improve the accuracy. Wearable technology is more compact and user-friendly. Smaller portable ECG device would facilitate seamless, continuous monitoring without significant disruption to daily activities, fostering early detection and intervention in diverse healthcare settings. Lastly, we can also integrate ECG circuit design with electronic health records and broader health information system to streamline the accessibility and analysis of ECG data.
In this study, we've developed a biosignal system for ECG recording, incorporating a right leg drive circuit, instrumentation amplifier, low pass filter, high pass filter, multiple notch filter, and the final output amplification. Our system accurately captures ECG signal between 0.01 Hz to 300 Hz. The system effectively produces a clean signal, closely resembling the input ECG. However, there are slight differences in output signal compared to input ECG, particularly in the distinctness of R peak and movement of the S point. Thank you for watching.